Now let's talk about under what situation we should choose BS law or Ampere's law to calculate the B field. We know that both are true all the time. And whenever we have a complicated current, we can always cut this while imagine cutting it into tiny pieces of elements with segment length of ds, and then use this equation to figure out the small contribution of dB every segment contribute, and then try to do the integration to find out the total B field at your observation point. You can always do that, but sometimes it's very, very tedious. Also, we know about Ampere's law, which says that if we are going to choose a closed loop, and then we are going to integrate the dot product of B dot ds along the loop, we are going to find out that no matter what, the integration result is going to be equal to constant mu0 multiply the amount of current enclosed in that loop, or the amount of current which penetrate the surface bounded by that loop. So we also know that in order to make this easy for calculation, to make it really useful, we should choose the loop in a smart way, which means we want either, for example, the B field to be parallel to the loop path. If B is parallel to the direction of your loop, B dot ds is simply equal to the B value multiply the small segment of ds. Or if the B is perpendicular to your loop, then the dot product of that B dot ds equals to 0. And we also would like to choose a loop so that along the loop, the B field is equal, it's uniform. So when we do this integration, B field is constant. Then we can take the B out of the integration. It becomes simply the B value multiply this integral of a small amount of distance along the loop, which become finally a total length. And this can greatly simplify Ampere's law and make it really useful for calculation. Let's now look at a few examples. First, if we have a short while which has a current going through it, we figured out that the B field created by this while is going to be into the page everywhere on this side and out of page everywhere on this left side. If this while is not very long, we know probably toward the center we have a denser and a stronger B field, and toward the end we have less contribution and less B field. And it's not easy to find a loop along which the B field is always parallel to ds or perpendicular to ds, and the B field is uniform everywhere. However, if your while is infinitely long and it has current I going through it, and then at any location along this while can be considered to be the center. Anything above and below should be symmetric, so that you know this current creates some B field here. It must create the same amount of B field out page on the other side at the same distance. And then surrounding this infinitely long while, everything should be cylindrical symmetric. And then we can easily find a circular path which has a radius of r, which is the distance from the location P to the center of the while, and coming like that. Okay, that's your path. And we know that the B field is going to follow this path everywhere. In that case, we find a loop which is parallel to the B field, so that the B ds become as simple as B multiply the total length of this loop, which is 2 pi r. And then you can easily solve the equation. We can also look at some other cases. If we have a ring which has a current I going through, and we know that it creates complicated B field along the center axis, it creates B field in that direction the total net contribution is that way. And the other locations, you are having B field this way, or bending like that, or like this, or like that, surrounding the loop. So it's really, really not easy to find B field to be uniform or along any loop, or to find the regular shape of loop so that B field is parallel to that loop. Same thing happens here. This while is going to create B field like, okay, surrounding this part, we have a B field into the page on this side, and out page this side, we have looping B field into the page like that, and then out page like this, looping and looping, and then here we have B field into the page on this side and out the page like that, and the looping and looping. And then at this corner, something becomes stronger or weaker, and here it's very complicated. You won't be able to really find something like that. Similarly, if we have a while and we loosely round it into that, we can see that the B field created by current like that is going to be surrounding the while. We have some B field into it, and out of it, so it's like this, and like surrounding this, like this, and like this. At the center, you may have something which goes all the way like that. But surrounding it, around the edges, you're having bending B field like that. There's no way to get something really, really uniform and parallel to the integration path. However, if we are having a very, very densely packed wires, okay, and then we know that inside, right-hand rule, we know that inside the B field is going to be uniform and straight. If the wires are packed very, very densely, so any variation around each wire, they will cancel out. You get uniform B field in the same direction this way. Okay, and in this case, it's going to be nice. We'll be able to find a loop. We can choose a loop like this. It is a right angular shape, so that in this part, the loop ds is parallel to the B field. In this part, it's perpendicular to the B field, and this part is perpendicular to the B field. We also know if this very, very densely packed wire is very, very long, it's a long solenoid, the B outside is equal to 0, and then this part gives the integration of 0. And then it also makes this integration durable and easy. We eventually find a 0 plus B multiply length of this particular L plus 0. Same thing happens here. If we have loosely packed wires and we bend it to form a circle, and the B field surrounding it could be complicated like this, like this, like this, like this, like this. However, if this wire is so densely packed, hundreds of thousands tons per meter, and then inside we know the B field is going to be forming loops. And then we can use that, choose a circle centered at the center of this coil to use that as the integration path. So, to summarize, when shall we use BS law and when shall we use Ampere's law? We really need good symmetry to use Ampere's law, in which we can find a loop which is either parallel or perpendicular to the B field, and the B field is uniform around the loop in those special cases.